You're live.
Since you brought it up, this is the George Will article. Wow. I don't want to get into a lot of details about this, but he describes what the Princeton Plasma Physics Lab does, and the fact that we actually have this capability. Now he basically says when, not if, when, decades hence, they and the collaborators succeed. Well, we're saying within the decade or thereabouts, right, we could actually get this done. And so I'll leave it there. But that's available. Did you make any copies of that?
I thought that you had them.
I just have one copy.
All right, it's not a big deal.
Anyway, what I wanted to go through is sort of the alternative to the collapse that's going on in the transatlantic system, which we're all too familiar with, and the fact that we're in a complete doomed situation right now. And the alternative is this Asia Trans-Pacific outlook. And what we're proposing is like the diametrical opposite of what Obama was talking about with this Trans-Pacific partnership, which of course has one gaping hole in it, which is sort of obvious if you think about it. It leaves out China. Now, you're talking about a Trans-Pacific partnership that leaves out 1.4 billion people? I mean, the point was it had nothing to do with Trans-Pacific partnership. It had to do with surrounding China and creating this situation where this conflict could be carried out, this military conflict. Now, on the 7th of December, our basement team did a video webcast, which was hooked up internationally on this whole Trans-Pacific fusion economy, as we call it, and how this would actually, what this actually would do, what is actually going on in China, in Russia, in particular, and how we could link up with this. Now, yeah, I mean, the main thing is that it's centered around this idea of this breakthrough that we have to get in fusion power. And some of you were here at the other presentation I made in terms of the nature of human beings being the quality of discovering the use of fire. No other creature has the capability of utilizing fire with any willful intent. And of course, what we're dealing with fusion power, the fusion process, is the same process that keeps all the stars going. So it's a fundamental principle. If we can master that principle, we've mastered a whole new type of fire, because it is the thermonuclear reaction that keeps the stars going. It's the basis of our life even existing. So it's really, it's quite profound. And of course, it also does redefine the whole idea of what resources are. As it's been pointed out, fusion is based on the idea of fusing atoms of hydrogen, isotopes of hydrogen, and you're releasing tremendous amounts of energy in the process, and then it ends up creating a helium molecule, or an atom. Now, to start off, I'm going to just put this little PowerPoint together, which shows a few things here. People are somewhat familiar with this, I guess, but we're talking about hydrogen, the most abundant element in the universe, which is fundamentally just a simple proton and an electron. That's what it is. Helium over there is the next. That's got the 2 protons and 2 neutrons, so it's slightly heavier. And then I'm going to discuss a little bit about the very familiar element called iron, Fe. Right? It's a lot of these abbreviations have to do with the Latin word originating these elements. Like Pb is lead. That makes sense, right?
Boom, boom.
K is potassium. That makes sense, right? Anyway, those are the Latin original names of some of these elements, known quite a long time ago. And of course, a lot of the elements were not even discovered until much more recently, and there's some of them are only they only can create in laboratories. They don't really exist in nature at all. That's what these particular elements down here are. But the main idea is that this represents sort of the basic ingredients of what we consider matter in the universe. This chart here shows you approximately how much the abundance of these elements really is in the solar system. Now the sun is by far and away the biggest chunk of any matter in the solar system.
What was that?
The sun.
Oh,
The sun, this actually says the cosmic abundance of the elements is derived from the spectroscopic studies of the sun, supplemented by chemical analysis of chondritic meteorites. And the point is that, again, helium is the most abundant, hydrogen is the most abundant, helium is next, oxygen, and then iron is over here, right? So I'm going to talk about iron in particular in a minute. But that's the most abundant elements is what this chart refers to. Now, in the case of iron, this is very interesting because this was presented by Ben Deniston in the this webcast on the 7th of December. And it's just taking an example of the uses of iron, particularly in the United States over the last, since the 1830s. He was making the point about the increasing power of us to utilize iron with what's called energy flux density increasing. That's the amount of energy per area per time that is going on in a process, right? Like in a blast furnace, for example. What's the actual energy throughput in this system? Well, if you're using charcoal in the 1830s, you've got an energy flux density of 2.6, and the average worker in 1 year can produce 10 tons of iron. Okay? And so this is the tons per energy measurement there. By the 1860s, we were using something called anthracite coal, which is a lot more energy dense than charcoal.
can you make that larger? I
I
can't read
really
anything.
don't think I can make it larger, no. Just pull the table
What's
back.
it say?
That's back it.
You see it?
We're gonna have to focus.
Would you like to move up?
This seat here?
No?
You want to sit
You wanna
over
move
here?
up here?
You can sit.
I know you wanna go
Sit up
up
front.
You wanna, Evelyn, you
Oh,
wanna
you
move
can't
up?
make it all right.
Right. Anyway, so then, this is 1900, it's called the Carnegie era, World War II era, the space program era, and what we could do in the future. But as you see, the amount of iron per worker per year is going up at a very rapid rate. You're going up to 21 tons per year per worker, 70 tons, 120 tons. We're at the height of the 70s era, we were producing 183 tons per worker per year of iron. It's a lot less now because we just have shut down all these plants. I used to live in Baltimore in the 70s when they had the Sparrows Point steel plant, and that was way down from what it was at the end of World War II. They had, when I moved into Baltimore in the 70s, there was 3 shifts a day, and it was about 6,000 or 8,000 workers. Now the whole thing is shut down. Yeah?
How do you measure the energy flux density?
Well, what it is the measurement of the energy itself, gigajoules per meter squared per hour.
But how do you get those numbers, 2.6 to 6.2?
Well, it's sort of like you're measuring the energy, the heat or whatever, through a certain area, like a flow of energy. You can measure it in probably electricity or other kinds of things, I don't know, there's different measurements.
Power technology is power and labor divided by flux density.
It's, yeah, it's the tons put out, the power technology is the tons of iron put out divided by the amount of energy put into it. That's it, that's actually quite interesting because you see that's increasing, right? The amount of tons per unit of energy is increasing.
So the 4 is equal to 10 divided by the 2.6, or,
Right. Yeah, right.
so then how do you get to 16?
Well, look at it this way. The power of the technology is that you're, for a certain terajoule of energy, terajoule being a measurement of energy, right? You're increasing the amount of iron being produced in the same amount of energy equivalent. You're producing more iron with a more advanced technology because you're increasing the temperature of the process. And temperature is sort of a good, rough thumbnail of what this energy flux density is. You're increasing the temperature of the process, you increase the efficiency of it, you actually produce more product, right? It's like the efficiency of a laser versus a candle, right? You could hold a candle under a piece of metal all day long and it wouldn't do anything, right? It would just get hot. But if you put a laser under it, it'll cut it right in two, right?
Can I say something? When I was working, one foreman shows how that is done. And each time they start up, they had these clocks that has all these charts in there. And as everything starts going to go to its peak, the numbers start going up. They used to keep records on these things. Each time they start up, each time they shut down, it changes the sheet. And it shows, you know, the level, how much you're putting in, how much heat is being produced, how much fuel you're burning, and then what it'll look like when you after you shut down. And on the other side, let's say if you're producing raw iron or steel, you know, what's coming out on the other end, and they have something to measure that. And that's how they get all these numbers. They have the charts and everything. And you also had to have a special calculator to calculate all this together.
Mm-hmm.
It's just, you know, the one guy was showing me that it was very technical, you know. You got all these
Here,
different-
I just want to go a step forward here because
Yeah.
what we're talking about is, this is one of the first, in other words, the use of iron became fundamental in terms of building railroads. And when they finally linked up the east and west sections of the transcontinental railroad, that was a fundamental breakthrough in human economy. And they were talking about something called a tramway of iron that would gird the world. Right? They were talking about that in this time, in Lincoln's time, they were talking about building railroad lines that would link up all the continents. And now what we're proposing is actually beginning to get accomplished. It's the idea of building a world land bridge, right? In other words, these are railroad lines highlighted basically that would link up all the continents, right? All the way from Africa to Asia to North and South America, right? And what's already underway is the Asian side of it. A lot of these routes are have actually been built. In other words, there are now railroad lines that go from South Korea, from China, all the way to ports in Europe. And it actually takes less time to get the goods across the railroads than it takes to take ships all the way around through the Suez Canal or whatever. Yeah. This is a picture of, just to give you an example of where this all came from, in a sense. In 1996, Helga LaRouche was at a conference in Beijing, China, and it was called the Eurasian Landbridge Conference. And then she visited this port facility, which is called the Eastern Terminal of the Eurasian Landbridge, right? So this was already sort of a going idea at that time. And then since that time, they've actually gone ahead and completed these rail lines. They've figured out how to interface different rail gauges and things like that across the continents, you know.
Electromagnetic?
rail?
Well, these are regular rail.
Freight rail, basically.
I don't know whether it might be electric or diesel, I'm not sure.
Diane, it goes into high-speed rail.
Well, that's different, that's another question. And this just illustrates why it makes sense to go across Alaska and Siberia to get to Asia. Well, because if you look at it from the top down, it's actually the shortest route. The Great Circle route cuts right through Canada, Alaska, into Siberia, and then to Asia. And the other part of it is this, which actually, of course, was discovered early on when we started building things like the Transcontinental Railroad, which is once you build these railroads, you're opening up whole new areas around the rail lines for productive activity. This is our design that goes back a ways. This was part of our Eurasian Landbridge report from 1997. But the obvious point is you have these high-speed rail, the maglev, or even regular rail. You're going to open up the basis for new cities, new manufacturing, agriculture, and a whole wide area on either side of the rail line is going to become capable of being developed. And that's what they're beginning to work on in Asia. For example, Russia is very serious about getting their side of this Eurasian Landbridge link up here. They're building this rail line that goes from here over to this port called Magadan. But then it's about halfway up to the next section of that to go up to the Bering Strait.
So would carry freight and supplies by rail be more efficient than carrying it by air?
Oh, absolutely. You can carry tons and tons and tons and tons and tons of freight on a rail, and you can't do that on an airplane. I mean, you know, have 100 cars of rail on a train, and it moves a whole lot of huge amounts of freight.
Is Vladivostok, oh, I was gonna ask you, is Vladivostok?
Vladivostok is down here.
Oh, way back there.
So this is part of Russia. This little strip
Yes.
down here is
Yeah.
way down. Yeah.
Because that was their only port. in
Yeah.
the cold weather.
So this is another element here where China is working on, and this, the next picture will be the Nawapa project we've talked about a lot. But this is in China. They've had this, to the point, the Chinese situation is this, that the southern part of China is has a lot of rainfall. There's a lot of water down here. A lot of it comes out of the Himalaya mountains, the Tibet area. All these rivers, like the Mekong River, begin here and they flow down here. The Brahmaputra River starts here and flows down this way to Bangladesh, and the Yangtze River here. So there's a lot of water down here, but it's very dry. It's arid up here, right? So their project is to move what they call move south water north. They're actually building these large tunnels or canals to divert parts of the river flow to the northern river, the Yellow River. And that's, you know, it's an incredibly large engineering project, right? Now this is very similar in the concept to what we're talking about here. Because here, we have all the rainfall up here, nothing down here. And the idea is to divert a huge amount of runoff from this area down into the desert areas.
Well, that's what Milwaukee is all about.
Yeah. Now, what do we have to deal with? We have some bigger problems to deal with, which is that, you know, our little planet is part of a solar system, which is part of a galaxy, and there's all kinds of forces at work that we don't completely understand. One of them is the fact that we actually have all these asteroids that are flying all over the place. They're not just confined to this asteroid belt between Mars and Jupiter. They often fly in and around close to the Earth. Sometimes they hit us, you know, like this one in Siberia earlier this year, right? And the Chinese landed this little rover. The lander was called the Chang'e 3 last weekend, and the rover is called the Jade Rabbit, or the other name for it is, the Chinese name is U2. But it's, the significance of this is many significant points. One is that this rover and the lander have a radar capability which can penetrate into the ground 100 meters. So they can actually study the terrain underneath the surface of the moon. And they've tested this in sites in China, in their mountains, and they've been able to figure out, groundwater versus ore and things like that. Well, there's no groundwater they have to worry about per se on the moon, not very much anyway. But they're going to be able to find out what kind of strata they're dealing with. Now, why would they want to do that? They're just up there to take pictures, right? They're obviously concerned about questions of resources and how do you mine these things. Well, obviously, what Daniel mentioned earlier was this idea of helium-3. And helium-3 is an ordinary atom of helium which has lost one of the neutrons. So it's it's 3 instead of 4. Ordinary helium is 4. It's got 2 protons and 2 neutrons, right?
That's a
So it-
alpha particle.
Well, here's the point. The moon, being a complete vacuum, being exposed to all this solar wind for billions of years, that has basically hit whatever helium atoms are on the surface of the moon and knocked off this extra neutron, right? So it leaves it, and it stays on Earth. All these helium elements tend to get completely absorbed or disintegrate or whatever very quickly. So you don't get this helium-3 on the Earth, except in very rare amounts, or you can produce it in laboratories and things like that. But on the surface of the moon, and I'll tell you in a minute how this got discovered, because it's important to think about where we should have been, where we should be, instead of where we are right now. This is a picture of the helium-3 reaction, deuterium being the helium isotope, which has an extra neutron. So it's the proton plus 1 neutron. It's called deuterium. And if you combine it with helium-3, which is 2 protons and 1 neutron, these 5 items come together and they release a regular helium atom and a proton and a whole lot of energy. That's the fusion reaction. And what's significant about this, unlike the other kind of fusion that I described the last time, which is using deuterium and tritium, which is what they do in the Princeton Plasma Physics Lab. They use deuterium and tritium together. The difference is that this ends up having 2 byproducts that are both charged particles. A neutron has no charge. And why is that important? Well, if you're going to control the byproducts of this reaction in a magnetic field, you need a charged particle. If you have a neutron, it escapes the magnetic field, and what happens is it basically destroys the wall of your fusion reactor. So they can't keep it going very long. So they can figure out a way to get this thing to react this way, so they have charged particles, then the magnetic field would hold all the products together. And then they could use them for generating power directly.
So this process is verified, is that right?
Yeah, this is,
So
all these laboratories have done, they've done all these kinds of fusion processes. The question is getting enough of it going in enough area in a concentrated way so that you're getting more power out of the whole process than you put into it to get it started, right?
So the problem is to contain it or make it big enough?
Well, there's a combination of problems. There's the containment, there's making it enough fusion reactions to go on. I mean, one single fusion reaction probably wouldn't, you might not even, you would hardly notice it, because these atoms are very small, right? But if you have a lot of them, then you end up getting a lot of energy put out. If you get a huge amount, you end up with what in an uncontrolled form is the hydrogen bomb. Obviously that puts out huge amounts of energy, right away.
So this process really relies on the source of helium-3. I mean, if you don't have.
Yeah, if you have the helium-3 in plentiful quantities, then you can do this kind of reaction.
You cannot synthesize helium-3?
Well, it's very it's difficult. Like I said, anyway, what happened was this. 40 years ago, this month, we had the last Apollo mission on the moon. And one of the guys who was there was this guy, Harrison Schmidt. Anybody know about him? Well, he was one of the astronauts. He was trained as a geologist, he was the only actually trained scientist who was an astronaut who went to the moon. The other guys were like test pilots, you know, Neil Armstrong. This guy was a trained scientist. And later on, he became a U.S. Senator, I think from Arizona. And he's become very good friends of us, because he's worked with Marshall Freeman, who you may know does a lot of the work on science and space. In fact, this is a book which I'll discuss a little bit later by one of the leading rocket scientists named Kraft Erika, who worked with us very closely until he died. And Harrison Schmidt wrote the foreword to this book. And Marshall Freeman was the person who put the whole book together. Now, this is a picture that they took during their 3-day excursion on the moon. We're looking at the Earth from the moon, so you can get a little perspective there. That's Harrison Schmidt doing some of his geology experiments. That's one of the little measuring devices that they used. That's another picture there. Now what happened was this. They brought back about 300 pounds worth of moon rocks in that particular mission. And in the course of examining these moon rocks, they discovered a large amount of helium-3 was in these rocks. So Schmidt has been making the point, and I think he was the most prominent person making the point, that this is a tremendous resource. We should be going back to the moon and developing this as a resource. Wow. So here we were 40 years ago. We were on the brink of actually making these kinds of breakthroughs, and the whole thing got shut down. You know, we didn't go back to the moon. We didn't do much of it. We had a space shuttle and a space station and things like that. And now finally the Chinese have gone back, right? Now, again, this gets back to this. What does he mean by the extraterrestrial imperative? That was his term. And Kraft Erika, by the way, he was the guy who designed and developed something called the Centaur rocket. The Centaur rocket has been like the main second stage of our rockets for 40 years. It's the last famous case of using the Centaur rocket was when they crashed one into the south pole of the moon to basically cause a plume of dust and all that to come up to examine it and find out that there was actually water accumulated at the South Pole. Frozen, of course, ice, but there was a huge amounts of water on the moon in the form of ice at the poles. They're in the crater, they don't get sunlight during any time of the year, so it doesn't boil off or anything like that. Anyway, so the Centaur rocket was Kraft Erika. That was like the biggest second stage rocket we had for 40 years, still being used. And he also had this concept that he said that the moon is actually like the 7th continent. And if you think about the size of the moon physically, the physical dimensions of the moon, I don't know the exact numbers, but it's like a big continent if you wanted to measure it compared to the Earth. Right? And we can it's only 2 days away. Why not, you know? And here what he's described, what this picture is about, I think he actually made these paintings. But anyway, this is like a huge fusion reactor on the moon. And the whole idea is that what he had was to hold cities on the moon, build fusion power plants on the moon, you know, construct the whole thing on the moon, and develop you know, industrial and other and scientific colonies, right? So that was the, that's the idea. And the idea of an extraterrestrial imperative is that it's sort of, what he really was describing is that this is like the next evolutionary step that mankind has to make. We're not just bound to be a creature on this planet. Our imperative is to go out there and become a multi-planet species.
Well, he says that we're like a fetus in the womb. We're like a baby in the womb.
Yeah.
When we're trapped on the Earth, and that to extend beyond the surface of the planet is as if to emerge from the womb.
Yeah.
Be born to it. Become. Yeah.
Yeah, that's what it does. Yeah. And I mean, again, this gets back to this idea of fusion, because what we're dealing with is not just mastering the principle of fire, which our ancestors successfully did, which is a chemical process, but actually mastering this nuclear process of fusion, which is what keeps all the stars going, ultimately which created life itself, right? So that's where we have to go. Let's see. Now, I'll just go through a few things to kind of contrast what's been happening. Under this current Obama administration shut down cutting of funding of all these fusion programs, where these fusion scientists are forced to choose, do you want this or that? You can't do both. They basically have shut down the one at MIT called the Alcator. And this is, was famous for having the highest plasma pressure of any of these fusion devices. So because they've shut it down, all the students who used to be in these programs are now leaving, and they're not, who knows what they're doing. On the question of nuclear energy, of course we're shutting down nuclear power plants. But China has 16 nuclear plants working right now. They're planning another 30. And they're also planning to develop something called a high temperature gas cooled reactor, which again, because it's higher temperature, you can do a lot more with it. You can use it, the higher temperatures, to process for industrial uses, for example. You can use the higher temperatures to desalinate seawater very efficiently.
That's superheated?
It's, yeah, it's like superheat, yeah. I don't know what the temperatures might be, maybe you know. But it'll be, you know, superheated steam or whatever. But now, who first developed the high temperature gas reactor?
Who?
Who did?
What country?
What country?
Is that Bessemer?
Starts with U and ends with A.
That's right.
Could that be USA?
Yes. Yes, right here. And we had one working from 1979 to 1989 out in Colorado. It's called the Fort St. Bering facility. It's now shut down. The other use of nuclear energy has been something that the Russians have worked on a lot, called the floating nuclear power plant, which they've been developing recently. But who, again, built the first one? We did. 1968, the U.S. Army nuclear program had a ship. It's just like what looks like a big freighter with a nuclear plant in it. So they could sail it anywhere they wanted to, hook it up to the dock, run their power lines off the ship, and you'd have a emergency power for a big city.
It's from the boat.
Yeah, right. It's a freighter, you know, a big freighter that can carry the weight of a nuclear power plant on board. I can get a picture of some of those here.
We were doing that in the Navy. When I was in the Navy, we were dealing with superheated steam, and the hazard was, you know, it could cut like a razor if you go, if it's from a small pinhole. If you go past it,
and it's a rupture, you know.
Yeah, it's high pressure steel.
It could decapitate you, you know.
Yeah.
But,
Now, going back to that picture of Helga, from 1996, from 1996 on, she was actually written up and noted in the Chinese media as the Silk Road Lady. Because this whole idea of the Eurasian Landbridge is called reviving the old Silk Road, the old trading routes that go back thousands of years from Europe to Asia, the Silk Road. And now the new president of China, I can never get his name straight, but
Xi Jinping.
okay. He's been talking about the new Silk Road, the Eurasian Land Bridge. He also visited the Chinese fusion experimental reactor, which is called EAST, E-A-S-T. And that actually uses something called superconducting magnets, not just regular electromagnets, but superconducting magnets. And he made a very simple statement of how fundamentally important fusion really is, as opposed to Obama, who made this idiotic comment saying, you know, what do we need this fancy new fusion for? We can just insulate our windows better. Insulate his brain with it. I'll give you another couple of examples here. This is there's a technology which people have been hearing about, which China has been making the most use of, and also Japan and South Korea. It's called magnetic levitation, maglev trains, which people know are trains that have no wheels. They float on a magnetic field. They're lifted up by the magnetic field and then propelled by the magnetic field. And of course, they have no real speed limit, but they have gotten up to like 300 and 400 miles an hour. Now, who developed the technology for this? The original sort of concept of getting it to work.
I guess.
Maybe the
Germans,
We did.
We did it.
Back in the
In
60s.
1968, a couple of scientists at Brookhaven Lab out here designed the technology, the basic, figured out what the combination would be to get this thing working. And I heard a rumor that they had calculated this when they were stuck in a traffic jam on the LIE. Maybe that's just a story, but anyway. And then
the next level is superconductivity.
well, superconductivity means you're having extremely cold temperatures surrounding your magnet, so that there's no loss of current, there's no friction, there's no resistance in the current.
Right.
So you can keep the magnet powerful with no heat.
Right.
Because most magnets, electromagnets, generate a whole lot of heat.
And that's lost, they're lost.
Yeah. And you can destroy the magnet just by the heat. It'll melt the whole thing.
Much more powerful too.
Right. Now, just in the basic terms of high-speed rail, again, we don't have any high-speed rail. We have slow-speed rail. People go high-speed, they crash, and they have accidents like that. Yeah. But China only began its high-speed rail program in 2007. By now, they have 5,000 miles or more of high-speed rail all over China, and they plan to have 10,000 miles by 2020. And by high-speed rail, it means they can travel a distance which is equivalent of going from Washington, D.C. to Houston in 8 hours. Okay? Now, Amtrak takes about 30 hours to go from New York City to Miami. Now, I mentioned that I showed you the picture of the Russian railroad plans to go all the way to the Bering Strait. And they actually have preparations being done right now. There are technically plans in the blueprint phase of building railroads from North America, Canada, up to Alaska, but that's all they are, it's just blueprints. There's no actual plan of anything like that to build our side of the connection. So, and then another example of how far gone we've gone is that, you know this company SpaceX that does these private launches of supplies to the space station? So it's a private company, it's not NASA, it's not the government, it's a private enterprise. It's successfully sending payloads up to the space station, right? Well, it turns out that they purchased their booster rockets from Ukraine. All right? They can't get the quality they need from anywhere in the United States.
Wow. Sad.
Now, again, I'll just conclude on that one, on the one note about this whole question of the asteroids, because the
There's just one thing that, when you're talking about the Asia pivot, a story that I really liked, that I heard not too long ago, was South Korea, that, as I understand it, 20 years ago, when they were having their first nuclear reactor built, the only thing the South Koreans were capable of doing at that time were building the housing for the engineers and scientists that were going to go into the actual work. And that now, but that was their commitment then, and that now that they are producing nuclear scientists and engineers, every year they have a graduating class now, some 20 years later. And they are, of course, in line with the Asia pivot that Lynn has been talking about. I don't know about any space program there, but in terms of their power and infrastructure and expansion, this small nation is really just shown. It's not just the cars, in other words, where they're advancing, right?
No, it's true. If we want to, if we actually decided to go ahead and build new nuclear power plants here, like to replace the one in Oyster Creek, we couldn't build. We don't have the steel-making capability in the United States to build containment vessels. We'd have to import them from Japan, or possibly South Korea, I guess. I don't know. South Korea. We don't have the. We shut them all down. You know, all these steel-making facilities.
Is there any way that we can protect ourselves so that an asteroid should never hit our planet?
I'm glad you brought that up. I'm glad you brought that up, because we better get cracking. Right now, no, we don't have any way of stopping an asteroid from hitting us if it happened to be something we saw that was on collision course with the Earth. If it was sufficiently big, we'd be in big trouble. The one in Siberia, Chelyabinsk, was fortunately only about 17 meters across or something like that. And that did a lot of damage, but nobody got killed, right?
Imagine if it would come down on New York.
Right. Now this is the point, though. You've got a huge amount of these asteroids flying all over the place. And one of the reasons why it's crucial to go back to the moon and to continue to put these rovers on Mars and possibly other areas is that we have to be able to figure out where all these objects are. There must be some pattern or process causing them to move in the way that they do. They're not just randomly flying around. There's some kind of an ordering process to this. And if we can understand that, it's like figuring out, weather forecasting, right? You want to figure out where the storms are coming. Are they coming up the coast, or do they come across the continent, or which way are they coming? So you can be prepared and deal with it, right? So in 2011, in October, the Russians made an offer to create something that they called the strategic defense of the Earth, right? The idea of this is a fundamental problem that all of humanity has to face. We should work together. It's a global initiative for a strategic defense of the Earth. We should have some kind of, global system. We can actually figure this thing out. And of course, this got even more intense after the Chelyabinsk meteor hit.
And that SDE for Russia came from Reagan's SDI proposal?
Yeah, and yeah, it really did, because again, that goes back to the fact that even at that time, we were concerned about that, and also the leading scientist, Dr. Edward Teller, who was working on this SDI program, had a series of conferences after the SDI was announced, where he said we should actually be concerned about the common interests of mankind, including utilizing, he was suggesting whether we could send nuclear rockets off to, blow up an asteroid to see what would happen, see what the capability was. So he was proposing that as well. Yeah.
So you have a situation where the Chinese are now on the moon. They know about Helium-3. They apparently intend to build fusion reactors using that Helium-3, which is a huge, very, very valuable source of fuel. Brings up the issue of mining rights for the moon. I mean, how stupid has it been for us to sit aside, and now the Chinese have moved in? Do you think they're going to say, okay, this is for everybody?
Well, I wouldn't, first of all, this is the moon. It's not like it's just going around the corner or up in some mountains. It's going to take an international collaboration to get any of this done. And that you got to have a sense of, is it, oh.
Yeah. Do you think they make any contact with different life form?
Are you sure about that?
Sure.
Pardon?
Do you think they make contact with different life form concerning the space program now? Because there's some deals.
I'm not going to even speculate on that. I mean,
It's the aliens here we've got to worry about it.
no, I don't know. I don't want to speculate on that because, first of all, at this point, I don't think we have any knowledge of anything like that. And although it's a big universe, it's a big galaxy, there's probably 100 billion stars in our own galaxy, so a lot of them have planets, and there could well be other life. But that, these stars are a long way away. I mean,
But it's starting, this project
I mean, the Chinese didn't send up a man to the moon, they
No.
just landed.
Right.
no, it's just rovers.
Right.
They're-
The thing that I find, again, this all goes back to Lynn, and that the greatest war avoidance strategy is development. And to see that that some of the I think people are underestimating for Putin's image on a global scale to be reversed as it has been, for people now ready to look at Russia more as a nation, like we are, as opposed to the Soviet fears and the Chinese fears and the oligarchs of that region, that there's a war going on within the against the oligarchs there as well. And since their aim is to control science, if you break them, then you have the chance to cooperate. And clearly, through the work of others, but with Lynn and Helga at the helm of this over decades, those scientists that are still alive and able to bring up another batch seem to me completely willing to pool together their resources, because it's the only way we're going to come out of it. Even if the United States had kept its leading edge scientifically, the universe is too large. You need all of mankind, the best of mankind throughout the globe to participate in its future.
Well, this is our point, which is that you're not going to get this breakthrough in fusion without having a global cooperative effort among all the scientists of various countries. And also, we can't get out of our economic collapse without having this cooperation with Asia right now. We just couldn't produce this stuff.
I'd like to pull together a few other things, so let's,
Okay.
all right.
Thanks,
Thank you. That was an excellent overview. I didn't know any of this stuff about Harrison. What's his last name? Schmidt. Harrison Schmidt.